A Postgres table should not need a duplicate search cluster just to rank text. ParadeDB adds a transactional BM25 index you can query from Python with psycopg. You'll learn how to upsert rows in Postgres and use ParadeDB BM25 search inside Postgres to return the top filtered result from live rows. I'm Professor Pi, teaching search and IR with simple Python. A lot of teams end up copying rows into a separate search system and then fighting sync and stale results. That duplicate pipeline adds complexity, latency, and failure modes. ParadeDB brings a BM25 style ranked index into Postgres so the application table stays the source of truth and ranking happens next to the data. Put simply, BM25 rewards documents that use your query words more often and downweights very common words. When that ranking runs inside Postgres, your usual where filters, tags, numeric thresholds, whatever, get planned together with relevance. The practical win is fresher search and fewer moving parts when you need a retriever for a RAG pipeline or a web app search box. We will build a tiny demo that connects from Python, creates a docs table, inserts 3 rows, creates a ParadeDB index, runs a ranked filtered query, and then updates a row to show the index reflects the change immediately. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we check we can reach Postgres and that ParadeDB is available for queries. This snippet opens the local Postgres database and confirms ParadeDB PG search is loaded. If your application rows already live in Postgres, the first win is avoiding a second search service before you even run a query. The psycopg connect call gives Python a normal database connection. Then create extension if not exists PG search makes the ParadeDB extension available in this database. The tiny select casts the extension name back through Postgres, so the check fails loudly if PG search is missing. The visible output shows the extension name that will power the ranked search steps next. With a working extension, we need some live rows to index and keep transactional. This example creates a small Postgres table and inserts 3 rows that look like retrieval documents. Search relevance work gets harder when the indexed copy drifts from the source table. So this step keeps the source of truth boring and transactional. The docs table has an ID key, txt text, tag metadata, and rake for filtering. Each row goes in through psycopg execute, using parameters for the values rather than string building SQL. Con.commit makes the table and inserts visible before the ParadeDB index is built. The visible output shows how many live Postgres rows are ready to index. Now we build the index, so ranking can be computed without a separate system. This code adds the ParadeDB index that makes BM25 style ranking available inside Postgres. The key design choice is that the index is built on the same docs table your application writes, instead of on a separately synchronized search copy. The create index statement uses using ParadeDB and includes ID first, because key field equals ID identifies rows inside the index. It also includes txt, tag, and rate, so text matching and common filters can be planned against the same search structure. The visible output shows Postgres can resolve docs search IGs, which means ranked queries can use it next. Next, we run a user-facing query that combines filters and ranking together. This snippet runs the first viewer-facing search. Match text, apply a metadata filter, then rank by relevance. Weak search often fails because filtering and ranking are bolted together late, or because scores come from a different system than the source rows. Here, txt asks ParadeDB to match the query text, rate greater than or equals keeps low-rated rows out, and PDB score ID exposes the BM25 score for ordering. The limit 1 keeps the example focused on the top candidate a retriever might pass into a RAG pipeline. The visible output shows the selected row ID and its rounded relevance score. Finally, we show how an update to the same table immediately affects which row wins. This example makes the search result change by updating the source row inside Postgres. The operational pain this removes is the lag between a database write and a separate search index refresh. Con.transaction wraps the update, and once that transaction completes, the next ParadeDB query searches the updated txt value through the same Postgres connection. The query still uses txt, poly, %s, and PDB score ID, but now the newly added word hybrid can affect which row wins for hybrid Postgres. The visible output shows the freshly updated row becoming searchable, which is the core baseline for transactional retrieval. In a real RAG system, this pattern lets your application read and write documents and immediately use the same rows for retrieval. Your retriever is now a single SQL query away from the latest data, which simplifies debugging and reduces end-to-end latency. It is an in-Postgres BM25 index that ranks and filters without a separate search cluster. Use it when you want transactional freshness, simple deployment, and tight filters alongside text ranking. One limitation is that heavy search workloads may still need specialized scaling, so measure before shipping large traffic. Tune the BM25 parameters next. For example, try adjusting BM25 K1B on your product descriptions or FAQ set to see how precision at 1 changes. If short, practical IR helps, subscribe and watch the other videos on retrieval and ranking.